Testing. All right, everybody there? Can you hear me? Can everybody hear me? Testing. 3.141592653589793233846 2643383279502884191. All right. Hello, everybody. Welcome to 162. If you're in the wrong classroom, you can now stand up and scream and run out very quickly. No? No takers? Okay. Can everybody come on in? There's a couple of seats still up here. I suspect we're going to have a full house. Welcome, everybody. So, my name's John Kubiatowicz. Most people can't figure out how to pronounce my last name, so they call me Professor Kubi. That's perfectly fine. Today we're going to talk about what 162 is about. So, how many people here have ever actually programmed an operating system before? Okay, a few of you. Anybody here ever looked inside of one or compiled one? Okay, a few more of you. All right, we're going to hope to fix that. By the end of this term, hopefully everybody will raise their hand and they will do so like, yes, it was the greatest experience of my life ever. Hopefully. But let's start a little bit at the beginning. So what motivates this class is something like this. Does anybody want to guess what this is? Yes.
This is a diagram of like the Windows architecture.
Okay. Anybody? That could be, but it isn't. Anything else? Yeah.
The Linux kernel.
Okay. I've actually seen things like that. That is a good guess, but it's not. Go for it.
The internet.
Yeah, it's the internet. Now, this is a little bit of an old picture, but what's interesting about this is, in some sense, I would say the internet is one of the greatest artifacts that we've ever put together as a species. It spans the globe. It even goes out into space a bit. And what's interesting is this extremely complicated branching structure mostly works, which, is totally surprising. And if this were 168, we would spend a lot more time telling you why that's surprising. But for this class, what's interesting is every one of those little points in this diagram represents a client of some sort talking potentially to everybody else. And on those clients are operating systems, and they have security problems, and they need to communicate, and they need to protect their data, and they need to do something useful. And wow, this is interesting and very complicated. And hopefully we're going to give you some idea of how to even think about this to start with. What's interesting about internet scale is in the early days, there were a maximum of 256 points on the internet because there was a byte that defined destination, okay? Then it went to IPv4 and things kind of went up. Okay, so somewhere in the 90s we had the first version of HTTP, and all of a sudden everybody was really interested in the internet. Okay, I guess they wanted cat videos or something, right? And you get up, and now we're kind of topping out at 3.8 billion or more independent points on that huge graph that I just showed you that can communicate with each other directly. And then behind each one of those is potentially thousands of other devices. So if you put NAT into this, you can add many more. So why 3.8 billion? What are we running into here? Anybody know? Yeah.
Global population.
That would be a great thought, but it's not the population that we're running into here. Yeah. Yeah. So we're actually running into some limitations of the way the internet works because addresses are 32 bits mostly, although V6 is kind of fixing that. But this is amazing. 3.8 billion directly connected devices, okay? They're all running operating systems. They're all broken in some way or another, and they're all trying to communicate with each other. And so they're really at the heart of it all. So operating systems, what do? Well, they're kind of many things. And actually what's fun, I guess, if this were a philosophy class and we were drinking a good beer or something, is we could philosophize about what an operating system actually is. we'll give you some ideas of what some people think it is today. But, roughly speaking, it provides some abstractions to applications like file systems and processes and threads and virtual machines and containers and naming systems and resource management, memory, CPU, storage. And there's lots of interesting parts in the middle that you get to get a taste of, like scheduling, like concurrency, like transactions, and, of course, security. I'm always a big fan of thinking about the security of systems. Too many of them, security is like a bolt-on that you put on because you thought maybe I better be secure, so let's add this thing, and maybe it's now secure, and, of course, it never is, right? So, for instance, something you do every day, right? What do you do when you search with your phone, okay? Well, your phone, first of all, reaches out to something called a DNS server, okay, to maybe resolve google.com or something like that. The servers talk to each other. They decide, given the human name, what IP address is related. And then your phone reaches out over the internet. Okay, what does that mean? Well, it means there's an IP address and there's a bunch of switches along the way, and somehow those packets kind of make it through the internet to the destination, which, when you think about 3.8 billion things, it's actually pretty amazing that even sort of works, right? I hope you leave today being at least a little bit amazed at how this stuff actually somehow works. Maybe it triggers some interest there, right? So your query goes across the internet, and then it hits a data center, Google, let's say, and in that data center, that packet goes through a load balancer, which takes that one IP address and chooses kind of what's not busy at the time, and then that query goes to a search index, which searches and creates a result page, which then goes to an ad server and adds the ads, of course. And then the result goes back. So many little pieces of this process that you take for granted every day. And all along this pathway, there are operating systems in there. Okay? Now, why should you bother taking CS162? Well, some of you are probably going to design and build operating systems in the future, your startup. How many people here have thought of maybe doing a startup someday in their life? Okay, a few of you. All right. How many people have thought about maybe working at startups or small companies? There you go. More of you. All right. You might actually end up designing an operating system. Wouldn't it be nice to know what it does? Many of you, many more of you, are going to actually write systems that use the core concepts of operating systems, and it'd be a good idea if you had some idea what you were doing. Okay, it's very easy to throw together a bunch of libraries, compile it, produce something, and have no idea whether it's working correctly or how it should work. Okay, and we're going to hopefully give you some idea about that. All of you are going to build applications that use operating systems. All of you. If for no other reason than you're in this class and you're going to build some applications, hopefully you do this after this term. Okay? And the better you understand the design and implementation, the better you can make it work. Okay? I'm actually a big fan of abstraction, which means you don't want to think about details you don't have to think about. But I'm also a really big fan of being able to peel back the layers and understand what's going on when you need to. Okay? And that's that second part that often gets forgotten. People forget that they should be able to peel back the layers and understand something about what's going on, especially when you're debugging and something's broken. Okay? So, today, we're going to take a stab at what an operating system is, and maybe what it isn't. We'll try to figure out why they're so exciting. Okay, I can tell you guys are all just excited, right? Oh, and then we'll say something about how the class operates and so on. Okay? All right. Interactive is important. Now, the first lecture is often, I sort of talk at you guys, you're not quite sure what's going on and so maybe there won't be as many questions, but I do like to encourage a lot of active questioning and interaction in the classes in general, and I'll talk more about that in a little bit. So, feel free to ask questions, okay? So, what's an operating system? So it's a special layer of software that provides application software with access to hardware resources. So this is one thing you could say. And what I'm showing here is hardware. which has many things associated with it, right? Disk drives, CPUs, memory, all sorts of interesting things. And what we're doing is providing a convenient abstraction so that the folks that are writing the applications don't have to think about, for instance, how do I take a bunch of individual blocks on a disk and somehow put them together into a file so that I think of the file as being a continuous set of bits, right? When you're reading and writing a file, you certainly don't want to worry about which blocks make up that file and where they are on the disk, right? That's a level of peeling back the layer that's absolutely not useful when you're writing applications, right? So the other thing that is important is protecting access to hardware resources. So if multiple users are all using the same hardware, we want to make sure that they only access what they have access to and should access. So, of course, we talk about security, authentication, etc. And then the operating system will help mediate communication. Okay. So lots of interesting pieces. And we'll peel back a lot of these pieces as the term goes on. You know, in the old days, you had switchboard operators who were connecting things up. And then you had computer operators. Okay? You might imagine this was a while ago, right? And all of them kind of go after the operating system. Okay? And believe it or not, I like to show pictures like this every now and then. Like, can everybody see where my arrow's pointing? That's actually a tape drive. Do you know what they did with tape drives? They stored information on them. You know what they stored it on? Tapes. Wow, that's a little weird, right? Believe me, it happened. Okay? So, what do you bring into this class to understand what's going on? You're bringing in 61C. How many people remember 61C fondly? Oh, let me rephrase that. How many people remember 61C? Okay. So when you took 61C, what you learned is you learned a lot about things like how to make processors work, right? What are registers? What are the, what are the arithmetic units? You talked about storage, maybe how memory was laid out. Okay? 61C was your first step toward understanding and peeling back the layers. Now, it was a very simplistic view, okay? For one thing, when you talked 61C, there was no comment about multiple entities running at the same time. There's this one thing it's running, it's using the hardware registers and so on, right? So, that's fine for your first class, but real operating systems don't operate that way, okay? You also probably talked about caches. We'll remind you of this. Maybe you talked about page tables. Did they talk about page tables and pages? Good. But the question might be, all right, so how do I take my 61C knowledge forward? Well, one thing is I start adding an operating system. And so one of the things that an operating system does is what I like to call the illusionist. All right? So it's giving you clean, easy-to-use abstractions of physical resources. Things like the view that you have infinite memory. Okay, which of course you don't. The view that you have a dedicated machine, like you thought about in 61C. Okay? The view that there are files or users or messages or these higher level things. Okay? And it's often up to the operating system with this illusionist kind of view of the world to really mask the limitations of the hardware. So the fact is the memory isn't infinite, but I can pretend that it is because the operating system will try to do swapping. Okay, and we'll talk more about that as we go on. So, for instance, going back to our 61C version, maybe we actually have a virtual machine boundary here where there's still processor and memory and networks and storage, but, just like in 61C, but what we do is we put on top of this an OS virtualization layer. And that virtualization layer is going to take all of these real things underneath and it's going to virtualize them and make them look like they're infinite. Okay, or like, despite the fact that there are many users on this system, I've got exclusive access. Okay, that's what that layer does. And so underneath the covers, there will be an ISA, which you also talked about in instruction set architecture. But above, we'll now get things like processes, address spaces, files, windows. Okay, now I'm not talking about Microsoft Windows here. I'm talking about, Windows on a screen. All right, just out of curiosity, how many Macintosh users do we have here? Okay, how many Windows users? Okay, how many Linux users? Okay, how many BSD users? A couple of you. Okay, good. All right. So, sockets, communication, etc., threads. So, one of the things that you're going to learn about very early in this class is this idea of starting with a program, where a program is the thing that you wrote and compiled. It's your software, and loading it in to become a process. So a process is really an instantiation of a program that's running on a particular machine. So what does that mean? So what you see here is the little green blob is your software that you've built and compiled and linked. But in order to make it into a process, what we do is we have to load it into memory in the right way so that the processor's instruction set is pointing at it, or registers, are pointing at it. And now the processor can actually start running this entity. So the process is an instantiation of a program. It's what happens when you start it running. Okay? And usually there's an OS involved in doing that. So what's a process? Okay, we're just going to do a couple of things here where we pop down some of these terms. So we'll talk about how it's an address space. It's a set of addresses. We'll talk about one or more threads of control. We'll talk about the additional system state a process has. And a thread is really what you learned about in 61C. It's got a program counter, it's got registers, it's got a stack. Those terms all ringing some bells, you guys? Let's try it again. Let's see if it rings, right? Program counter. All right. Registers. All right. Stack. Oh, yeah, okay. All right. Now, you've all done some sort of task viewer or whatever in an operating system, and you see all the tasks that are running or the processes that are running. We'll talk about the difference there when we go further. But what this ought to do, and you ought to do this, if you haven't done this recently, and take a look. So this is something David Culler did last term. I just kept his slide. But if you look here, there's 20 or 30 things that are all running. These are processes that are all running on the same piece of hardware, and they're all able to act as if they have sole use of the hardware. So that virtualization gives us the ability to have all these processes. Now, you might say, well, why would I want them all? Well, we'll get to that. Each of these are doing something different, and it's much easier for the programmer to write the code that's running here if they have a virtual machine abstraction. Much easier. Okay. So, now, once you've got processes, then you can talk about once you have a process, you can talk about how can I have more than one. So here we have the green is running, right? And it's got the program counter and the processors pointing at the instructions in the memory. And all of a sudden, the timer goes off, and we do a context switch. So notice what happened there. I copied the registers off somewhere, and they're still pointing at the piece of memory that is the green process, but now the operating system's running. So that CPU, like you've learned about in 61C, is no longer being devoted to the green program or process. It's being devoted to the operating system. We've switched the context. And you will learn a lot about how contexts switch. Okay? And in fact, once we start being able to switch from a process to the operating system, now we can have many processes. And we can have many things running at once, just like that slide I showed you earlier. All right? Now, so really, another thing that the operating system does is it acts like a referee. So you get to manage resources, give protection, isolation, etc. You can decide kind of what fraction of the memory goes to a given process, or what fraction of the network bandwidth goes to a given process. Okay, that's the referee. So, for instance, now that we have context switching, we can start thinking about scheduling and protection. So there's the green thing, but gee, we have an orange and a red process. Okay, and so now what is scheduling? Well, scheduling is when I decide that the CPU should stop focusing on green and start focusing on yellow or red. Okay, and I can make decisions. Well, there is some quality of service metric I care about. This is running the brakes in my car. And if I don't switch from green to orange fast enough, I crash into a tree, which would be a bad thing, right? I'm assuming. Okay. So when we have quality of service metrics, we can start talking about how do our schedulers make sure we meet the quality of service metrics. Okay, you'll learn about that in this class. Protection. Well, this green memory has some cryptographic keys in it, let's say. How do I make sure that the red process can't look at green's memory and pull the keys out, right? Because if it does, maybe suddenly whoever owns the green blob, we can breach their bank account or whatever, okay? So that protection of memory comes into play. Does anybody remember how memory is protected? Go for it. Oh, in the front. Go for it.
You have the page tables and
Great. So we'll learn about page tables. The short answer is we translate the addresses that the CPU is using so that no matter what red does, it's never able to actually touch or modify green's memory. Translation. Okay, great. Any questions so far? Is this going to be on the exam? Was that the question? Oh, no, sorry. So really, you can think of the operating system as putting a protection boundary over the hardware and giving us all these cool abstractions and scheduling and protection and isolation. Okay. Now, I'm sure there are some of you sitting out there saying, boy, this is a lot of details. How am I ever going to catch it all? Okay, and that's kind of my job. So we're going to deal with each of these different things as we go. And I hope by the end of the term you'll have a very nice mental model of what's going on in an operating system and can figure out how to piece them all together. Okay? So the last thing that I like to talk about when we talk about what's an operating system is really glue. Okay, an operating system glues together a bunch of common services in a way that's convenient for the programmer. So what are common services? Storage. We talked about file system earlier. Windowing system. Networking. Okay, TCP/IP is a great example of a service. Sharing, authorization, that's security services. Look and feel. Okay, the look and feel of your system. How many people have ever heard of the famous look and feel suits of the 90s? Okay, yeah, a couple of you. You might find this amusing. Did you realize that Apple sued Microsoft because Microsoft's Windows operating system had the same look and feel that Apple's operating system did, look and feel. And so they were trying to get the courts to say that Microsoft had to either pay Apple a lot of money or cease and desist. Okay, because what was the look and feel? The look and feel was Windows, mice, icons, arrows. Now think through that for a second. What would have happened if some company, even Apple, who I'm sure we all like a lot, had managed to win that suit? All of a sudden, nobody else could ever do anything that had Windows in it, or mice, or whatever. Okay, now I've sort of given it away. They lost. And that was a great thing. And it was also particularly ironic because Apple didn't invent Windows or mice. Does anybody know who invented Windows and mice? Xerox PARC. Okay, so the look and feel suit of the 90s. So OS basics also include I/O. So for instance, what you see down here are things like networks and displays and, GPUs to do graphics and disks to do storage. And so basically what happens, for instance, is when we're starting a process, we have to grab the data out of the storage and put it into memory, okay? Or packets coming off of networks put into memory. Okay? And there's a whole interesting bus layout behind that. And I'll say a little bit about that if we get to it toward the end of the term, the end of the lecture here. But suffice it to say that buried underneath your view of an operating system is a lot of pretty interesting buses and caches and controllers and hardware. And I encourage you, by the way, to take 152 and think about that. Okay, I love that domain as well. That's not this class. But this OS virtualization helps to hide the important details of how the actual pieces of hardware connect with each other from the users that are trying to just get their job done and run programs. Okay? All right. So for instance, when we're creating a process or loading a program, what happens is the program's actually on disk. The file system in hardware has been, or the file system that's running in the OS uses the individual blocks on the storage to store that. We load it from the storage into memory, and then we launch the process, okay? All right. So what makes operating systems challenging and exciting? Okay. Well, how many people have ever been in one of our systems classes and not seen Moore's Law mentioned? Anybody? So Moore's Law, unfortunately, has been running out lately, but I will tell you that one of the reasons operating systems are so amazingly exciting is that for many, 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 many years, we had basically a doubling in transistors every 1.5 years. What that really meant was you could put more and more and more and more on the same chip, or you could make a much smaller chip that did the same functionality, a lot less power. And as a result, we have very interestingly complex systems out there now. That 3.8 billion nodes on that network I showed you earlier, why can we do that? We can do that because Moore's Law gave us the transistors. And so now, somehow, in a class like this, we have to figure out how to tame all those transistors and actually make them work for us rather than making things complicated. Okay? And I will point out, by the way, that at the far extreme where we are these days, even the transistors aren't always reliable, and so you've got to start dealing with a lot of failure. Okay? How do you make something appear to run without failure when all the underlying components underneath are failing? That'll be an interesting topic we'll address in a little bit. Okay. So the other thing that was kind of interesting is at the same time that Moore's Law was going on, and we're doubling our transistors on a regular basis, computer architects were making things faster. Okay, and so up until about 2002, we were essentially doubling the performance of compute every couple of years. Okay, and that was pretty amazing. So it was this is the years that people were lazy. Okay, what do I mean by that? These are the years where you build some software, it's not fast enough, you just wait and buy the next computer and it'll be fine. Okay, so these are the years of people being lazy. And then all of a sudden, physics came into play up at the top there, and now Moore's Law is running out, and we can't make things faster. Okay, and so what do we have to do? We put more things, but now we got to spread them out, and we start building complicated distributed systems. And that's kind of, as we go further in this class, we'll talk about, okay, I can't make individual things faster, but I can make things out of many distributive components. How do we do something interesting out of that? And we'll talk about that toward the end of the term. Okay? So by the way, if you take 152 or 151, you'll actually they'll talk a lot about the fact that all of a sudden, since the individual processors weren't getting faster, this was kind of the era of multi-core. And now pretty much you buy a cell phone, you buy a laptop, they all have 4+ cores on them easily. Okay, so there's a lot of parallelism that's just there even on a single chip, and complexity rules. So another challenge which I think is kind of interesting is one of the reasons of that fall off is that the amount of heat on each individual chip, by the time we reached the 2000s, the power density started getting pretty high. And if we had stayed on the original Moore's Law curve, okay, we would have basically had things that were kind of the heat of the sun's surface in your laptop. Believe me, that's probably uncomfortable. Okay? So that's another reason why they stopped making things faster and just started putting more things on a chip. Okay. So back in 2007, ManyCore Chips really arrived, and that was where we started having things like 80+ cores. Intel made clouds on a chip, okay? And the interesting thing that we used to joke about when this first started happening is how do you program this thing? Well, you basically have 2 CPUs, one for audio, one for video, one for the word processor, one for the browser, and 76 left over for virus checking or something like that. So people didn't really know if I've got a big processor with a lot of CPUs on it, what do I do? Okay, and fortunately, people have come up with more programming models that things work a little better. They can figure out how to make use of those other than just wasting them on virus checking. Okay. Parallelism at all levels. Okay, so, and then of course, all of this was great and Moore's Law ended. And in the original way that Intel thought of things is they would do a tick-tock process where they would change the process to something smaller transistor, and then they would change the architecture, and they'd keep alternating. And that happened frequently, and things got really fast. And then now these days, things are much slower. Okay, you maybe change the process occasionally, you change the architecture more frequently, you optimize all the time. And so it's much harder to be a computer architect these days. And pretty much to get that really small transistors that are really high end, only a couple of companies even do that anymore. Okay. So the other interesting thing, I think, is that hard drive capacity keeps growing to the point that today you can basically have ridiculously large drives, so ridiculously large that what are you going to do with them? Okay. It's what's kind of interesting is I saw. I'll show you later in the term. There's an SSD drive that's like flash memory that basically has 100 terabytes in a small little drive. Okay, that's a lot of data. Okay, what are you going to do with it? Well, I don't know. That's a lot of bits to protect. Maybe you put a lot of videos on it. I don't know. What else do you do, right? That's a lot of cat videos, okay? Or dog videos if you like dogs. And, of course, network capacity keeps going up. So we have lots of networking, lots of storage, CPUs everywhere. What do? We need 162. Okay? All right. Now, the Internet scale, over 3.8 billion users. It's kind of interesting. Sometime you might take a look at the statistics on that. Right now, or actually I will say back in 2017, we kind of had a 54% penetration of the world population for connectivity, so that somebody mentioned earlier that it was the number of people was the limiting factor. In fact, we haven't quite reached everybody. So there's significant parts of the world that still don't have Internet access. Okay. And of course, not only PCs, but lots of other things are connected. And then, of course, this is my favorite graph. So this one you might not have seen quite so often. This is called Bell's Law. This is the number of computers per person. And if you look way back when, you might have basically one computer for 1 million people. These are orders of magnitude. And kind of each decade, you sort of had a new type of item. Okay, and now we're at the far end where you might have thousands of CPUs for each person in this room. Now, if you think about that, even your cell phone's probably got 8 CPUs. If you got a car, it's probably got 100 or 200 CPUs in it. They add up really quickly. Okay, and this notion of the Internet of Things, which we will also talk about later in the term, potentially has sensors everywhere in the walls, etc., that are working for you. So when you come into a new environment, the vision, which is not all that far away, is that your cell phones or other items that are on your own person reach out to the local environment and negotiate compute for you, negotiate local storage, and potentially sensors, what have you, in the room, and you can basically on the fly craft an application. Okay? That's actually not as strange as it might sound. Okay? It's coming up. And so what's interesting there, of course, is this is driven by this fact that we can make small, fully functional things running operating systems that are at the low end of the scale and can be placed anywhere. Okay, and Berkeley is well known at all levels of this, by the way. We've got everything from high-end computing work down to and cloud computing work down into little motes and IoT devices. So you're in the right place for this kind of thing to be happening. Okay, lots of exciting applications. And lots of time scales. Everything from cache references that are in the sub-nanosecond range up to keystrokes that are 100 milliseconds or more. So the reason I put this up here is I want you to see the vast difference between different time scales in your CPU that you're carrying with you or your cell phone. That's a lot of zeros of difference. And that means somehow your operating system has got to deal with that wide variety of rates. High rate stuff, low rate stuff, high performance stuff, low performance stuff. Okay? All right. The other graph I like, which is kind of the inverse of the one I just showed you, is the Internet of Things scale, where at the low end we've got little tiny sensors, and as we reach out, the other end of the Internet is our huge clusters. Okay, we all know about the cloud, but did you realize that pretty much everything in between the little motes and the cloud are all connected to each other and functioning together? And so I'm hoping to give you a little bit of a view as we move forward about how to think about systems like this. How do you think about something at this scale? Okay, and most of you, how many people have a smartphone? Okay, most of you. So when you sit down and you type something on your smartphone, what's interesting about that is what you're doing kind of involves the phone, it involves the local cell towers, it involves things in the cloud. That's at least 3 levels. Okay, and as we move forward, I would say that it's going to start involving more and more levels. All right. So let's pause for a moment. Who am I? All right. Well, I already mentioned that I'm Professor Kubi. Before I came to here, I was at MIT. I was designing some of the first pieces of hardware that did both shared memory and message passing in the same chip. This is actually a chip I designed. Okay? I won't tell you how many transistors are on it because it's a small number relative to today. I have a big background in operating systems, so among other things, I worked for Project Athena at MIT, which was one of the first projects that tried to build distributed computing into the infrastructure. What do I mean by that? Well, what are you used to today? You're used to sitting on your laptop, reaching out to storage that's over the network, interacting with services. That's just kind of, you do that every day, right? Back in Project Athena, that wasn't done every day. And so we did all sorts of things, like developed new operating system drivers and network file systems and Kerberos authentication, and all that came out of Project Athena. I also worked on something called the Tessellation Project here at Berkeley, which was a ground-up operating system that we worked on from the ground up. And then what I was most well known for when I first got here is peer-to-peer systems. So I had a project called Ocean Store, which was one of the first cloud storage systems, back before anybody used the word cloud to talk about computers. And one of our important metrics was, for instance, how do you store data for 1,000 years? And we'll talk more about how you can use erasure codes and other things like that to potentially store your information for a very long time. And there are also some very interesting peer-to-peer systems like Tapestry and Bamboo that came out of our project. Somewhat most recently, I've been working on projects related to the Swarm Lab. I have a brand new project which basically is called Fog Robotics on the global data plane. I'll tell you more about that. But we're basically trying to change the world by altering the abstraction at which people talk about with the network. So rather than talking about packets, they start talking about coherent chunks of information, which we call data capsules. And we'll say more about that as the term goes on. And, lest I should not forget to mention this, I also do quantum computing, which is a little out of the scope for this class. Sometimes the final lecture, people get to choose what topics they want to talk about. Occasionally people ask me about quantum computing. It has been done. Okay. So we have 8 TAs. Are they here? Whoever's here, can you guys stand up for a sec? I guess they didn't all make it. Let's give them a hand. At the very end of the term, last class, we'll say stand up. We'll give them a hand again because you guys will have such a great term. But we have a very good staff this year, and so I'm really excited about how this term's going to go. So the sections that these TAs are running are still, I think they actually may have been assigned, but I will say TBA for now. You already know where everybody's going to be? No, they are TBA.
Oh, wait, no, all of us.
All of you guys?
We do, it's on the website.
Okay, yep, so they're already up on the website to see what sections. All of our sections, by the way, are on Friday this year. I know there was a question about that, but that's kind of where it is. Our infrastructure, is there's a website, 162.eecs.berkeley.edu. There's a Piazza, which everybody has found. And there's a webcast, tentatively. There is something I did want to talk about. So the webcast is really intended as a learning aid. I would say that you shouldn't be assuming that the webcast is a replacement from coming to lecture. It's been actually our experience that people that only watch through the webcast miss a lot of important things and get behind pretty quickly. So I would strongly encourage you to not assume the webcast is your sole interaction with the class. And I'm assuming for a moment that the people that might apply to are waiting for the webcast to come out. It will not be immediately after lecture. I'm thinking I probably will keep the webcast since we said we would, but it might be a little delayed. And I will tell you, it's not always doesn't always work. So, textbook is the operating systems textbook, Principles and Practice. It's pretty good. I definitely recommend it. There's another optional text, which I forgot to put the slide up here, which I will mention when we need it. All of this information is actually on our resources page of the website. There's another book that is the one that we used to use for 162. It's got a slightly different way of explaining things, and I have found that if the way of the first textbook doesn't work, the second one sometimes helps. And the second textbook is pretty cute. It's got dinosaurs and so on in it, so perhaps that helps. And then there's a lot of online stuff, okay? So this website here, I encourage you guys to look past the schedule, which is still a work in progress, by the way, because on the resources page, we have things like research papers and books that you can read and things like that are really intended to help. Okay, and in particular, and I'm going to say more about this in a few slides, this class is pretty heavily reliant on you understanding the C language. Okay, now that's the language C. Okay, it's not B, it's not C++ in this class. And so this is very important, and we're going to try to front load your memory on C from 61C. And so we actually have a homework 0, which is going to be released soon, hopefully before midnight. And we're going to have a review session on the C language next Monday. I'll say more about that, but you've got to get up to speed quickly, okay? The syllabus is a bunch of OS concepts, basically helping you to understand how to navigate as a system programmer, so process, I/O, networks, and virtual machines. Concurrency we'll talk about, threads, scheduling, locks, deadlocks, scalability, fairness. We're going to talk about address spaces. You saw a little bit of their utility earlier when we were protecting green from orange and red, but we'll talk about virtual memory, address translation, protection. We're going to talk about file systems, I/O devices, file objects, storage, naming, caching, all of these interesting things. My particular storage is my thing, okay, because I believe that our data is the most important thing out there that we need to protect. We need to protect it from breaches. We need to protect it from bit rot. There's many things because the data is society in some sense, and so we've got to make sure to protect our data. And so we're going to talk a lot about that as we go forward. There's been far too little focus on how fragile information is as operating systems, so we'll talk about that. Distributed systems, we're going to talk about protocols and RPC and NFS and DHTs and consistency, scalability. All of these terms will mean something to you later. How many people have run into distributed hash tables before? I think we used to do those in the 61Cs. Well, we will learn a lot more about them, okay? We'll talk about reliability and security, fault tolerance, protection, security, okay? So some of some of these topics we can only really touch on, but I'm hoping to give you enough operating knowledge that you can then go into a class like 161 or something like that with a good idea what needs to go forward. Okay? How many people have taken or are planning to take 161, just out of curiosity? Good. How about 152? Got a few of you. Good. 168. Networking folks? Okay, good. So all of these classes kind of revolve around 162, okay? Because the hardware is underneath, the security protocols are on top, and the operating system is smack dab in the middle. All right? And so having a good idea what that layer is about is going to be helpful. All right. And we'll talk about the cloud, of course, but we'll also talk about the fog, if you can imagine what that might be. And we're not talking about San Francisco on a early morning. We're talking about something else there. Okay. So this class is learning by doing. So there's 3 projects. They've been rearranged and simplified a bit last term. We're going to stick with mostly with what happened last term with some tweaks. There's a user program, so you're going to start kind of at the how do you use these things, and then second project will be in threads and scheduling, and third project in file systems. These projects I'll talk about later are done in groups of 4, so we're going to assume that you're starting to form groups even as we work. One of the things that we are trying that's new this term is we've split the homeworks that used to be really large things into 1-week chunks that are a little more digestible, with the sole exception of the first one. Okay, the first one, which I call homework 0. I'm a computer scientist. I can start with 0, right? And homework 0 is actually a 2-week thing, and it's going to be handed out tonight. Okay, and you should get going on it tonight. Okay, question? Yes. These homeworks are going to be in our auto grader, and they will be, which you'll learn about in homework 0. But I think we do support Gradescope. Written things will go in through Gradescope, but these projects and homeworks will be mostly gone through the auto grader. That's a good question. The reason we put things through the auto grader is we can automatically test functionality, make things work, make sure things work. All right. Any other questions? All righty. So, I hope when you get out of this class, you will have some significant skills in how to program systems. Okay, you will hopefully learn C. If you don't, you're going to be in trouble. You will learn how to use Git. You'll learn, how to build parts of an operating system. All right, you will actually have a skill set that comes out of this, and it's worthwhile. And it will be a skill set that you can basically transfer to a wide variety of interesting things. And I will point out the reason I highlighted the last 2 homeworks in red, they're really kind of part 1 and part 2 of the same homework, is we'll even be looking at Go a little bit. Okay? Yay! Boo! I don't know. Go is an interesting language that has been catching on in parts of the Valley, and so you'll at least get a little bit of a chance to play with it. All right? I don't know that there's any time soon that we would do the whole class in Go, but certainly you get a little chance to do some of this at the very end. All right, any other questions? Good, okay. Learning by doing. So what does this mean? Well, our projects are actual construction projects inside the operating system. So we're using an operating system called PinTOS, which is a real honest-to-goodness operating system that you could boot natively on hardware. One of these days, maybe this will be the term, I don't know. I have been thinking about actually having you guys copy a bootable version on a little memory stick so that you can put it into an actual laptop and boot it. How many people think that would be cool? Okay. Well, we'll see. But the thing you should get out of what I just said there is this is real. Okay, so you're going to get to play with a real operating system. It's stripped down, but the problems and solutions that are inside of PinTOS are actually real problems. And so you as a group with 4 members are actually going to get a chance to tackle some of these problems. And by the way, I don't know how many people here have seen The Search for the Holy Grail, but what we're talking about here is this is like the Holy Hand Grenade, right? So there can be 4 members in your group, not 3 and not 5, okay? Okay, you can get to 4 by counting through 3, but definitely not go to 5, okay? So we're looking for 4 members, all right? And communication, cooperation will be essential in your groups. There's going to be design documents. There's, you can use online tools like Slack or Messenger or whatever, but I hate to tell you this, you need to actually meet with each other in person. Okay, and I realize this violates all precepts of modern society. However, it has been my experience that groups that attempt to talk only over email end up in serious trouble by halfway through the term. Okay? I realize that just doesn't make sense. It seems like it shouldn't be that way, but it is. I think when you put your groups together, plan on meeting a couple of times a week physically. Okay? You'll be much happier, and, you can check out all the great coffee that we have floating around Berkeley here. Okay? We've got the new coffee house in Echeverry. We've got Pete's. We've got all sorts of stuff all over the place. Meet in different coffee houses and have good coffee. Or if that's not your thing, tea. Or you could go to Jupiter, but probably shouldn't go down there. Okay. So, think of this project group as you're trying to make it work like a smoothly oiled machine. So figure out how everybody can do work and have clear responsibilities. And you will actually evaluate your teammates at the end of each project as to how they have been doing. Now, we use this to help us understand group dynamics. Okay? But it's important to try to make things functional. Okay? And dividing up by task is probably not a good approach. Oh, yeah, you do page tables, and you do scheduling, and I'll do, I'll bring the coffee. I think it's better to sit down as your group and try to figure out how to make it work. There is a lecture that I sometimes give. I haven't for a number of years, but maybe I will. A few slides that talk about sort of ways of scheduling groups. Would that be interesting to anybody? Maybe a few slides. Most important high-level bit that you should get out of what I'm talking about here is meet together. If you meet together, you're already like 50% of the way to having a functional group. Okay? And of course, one of the ways you confuse what you're doing is this is like in industry, you're working together, you're communicating with a supervisor who's your TA. You're going to be making basically discussions about what the team's plan is, what are the responsibilities. You're going to be giving short progress reports and design documents just like you might do in industry. Now, that isn't because it's just like what you might do in industry. It's because it is the way we believe is a good way to make sure you make progress. And so this is hopefully helping along those lines. All right, any questions? Okay. Now, how many people have noticed the fact that we have a periodic table on the wall? Okay. All right, a couple extra points. How many people could recite the first few lines without looking? Don't forget your surroundings. All right, so how do we get started in this class? Homework 0. All right, by the way, I love teaching this classroom because, I don't know, the idea that I'm teaching in a classroom with a periodic table on the wall always struck my fancy a little bit. I don't know, my dad was a chemist, so maybe I like it that way. But start homework 0 right away. Hopefully today, as soon as it's released. What does that get you? It gets you a GitHub account, registration, survey, Vagrant, VirtualBox setup. Get familiar with all the 162 tools. Submit AutoGrader via Git. If you make it through, let me rephrase that. When you make it through homework 0, you will actually have launched yourself on the path towards being ready for 162. Now, part of this homework 0 is recalling how to program in C. Now, I realize that C doesn't have a lot of emphasis in 61C as it used to, even though there's a C in the title. So like I said, there's actually going to be sections on Friday, this Friday, next Friday, which are unassigned so far, so you could attend any section you want. After a week from Friday, we're going to assign sections based on your groups. So all of your group needs to be meeting in the same section or at least with the same TA. Okay, but until then, for the first 2 weeks, you're going to go to, I would go to the Friday section of your choice because we're going to be talking about things like C. Okay? We're going to be helping remind you of the tool set you've got to use. Okay, so these are kind of, unlike most of the sections maybe you run in here, these are actually useful sections, right? How do I do stuff? I'm kidding, of course. But the reason this is very important, and I want to say this up front, and please tell your classmates who aren't here today for some reason, there is an early drop deadline in this class, which is a week from Friday. So on the 31st, you get to make your decision about whether you're out or in. Okay? And since there are people on the wait list who want to get in here, and then people on the concurrent enrollment list who really want to hope that the wait list goes away, if you're actually thinking you don't want to take this class, please drop early just so that other people can get in. I'd like to take everybody I possibly could, but the room has got a certain size to it, and we've got so many TAs, and we just can't. So, but on week from Friday, you get to decide if you're all in, and then you're all in. And it'll be great because this is an awesome class. If you're on the wait list or concurrent enrollment, we've masked out the sections and the TA support. There's some possibility the class size may be increasable a little bit, but not by much. Unfortunately, is there anybody here who is a concurrent enrollment person? A couple of you. Well, you're at the low after the wait list, so I don't know how this works. Sticking it out might not be bad if you're willing to. I can't make any guarantees that you're in, though. Okay. Are there any other questions? And in fact, Alex, what we'll do is I'll send you the concurrent enrollment students so that you can put them in the system at least. So we'll make sure that if you're concurrent enrollment, you can at least do homework 0. Okay? All right. Are there any operational questions? No. Okay. So, C. Okay, so C is a great language for writing operating systems in. Regardless of what you might have heard, it's at least a language that a lot of operating systems are written in. I'm willing to go that far. But it's a really low-level language, and it's not one that many of you have experience with at this level. So things like pointers, memory management with malloc-free stack, etc., debugging with GDB, these are things that if you are willing to put in the time in these first 2 weeks, it will pay dividends the whole term. Okay, I've taught this class many times. I've seen people who try to make it all the way through the class without ever actually learning how to write C. And this is painful for everybody involved, and so I don't recommend it. You're going to be working on a larger, more sophisticated code base than anything you've seen. Don't let that scare you, because big code bases are the rule of thumb for what you're going to do in your future. They're all organized properly, assuming they're well-written code bases. So it's not about the size as it is about how you approach it and how do you find the abstractions and how do you find the parts to understand the high level. This is really a skill that I believe pretty much anybody who's willing to put in the time can figure out how to parse something like an operating system, and that's part of what we learn in this class. But if you don't understand the language, you're going to be in trouble. Okay, it's going to be hard. And so, in addition to the 2 sections, we also have a review session on C next Monday. Okay, so this will be, exciting. You can go there, you can ask questions, you can see one of your TAs presenting the joys of C as a language. And hopefully, by the end of the 2 weeks, we're good to go, and now we can get into the real stuff. All right? So, homework 0 is really something that I would get going on, and we have TA resources devoted to it, et cetera, just to get you up to speed. There's a resources page on the course website, which actually has ebooks on Git and C, which you can use. There's also this beta C programming reference called Ladder, which is available as well for us to help you along. And the first 2 sections are dedicated. Okay, I sound like I'm belaboring the point, but I just want you to get going so that we can get on to the important stuff. Okay? Learning another language, programming language, something that all of you have done a couple of times with different languages. I believe you can do it here too. Okay, so treat this as a challenge that's fun, not something to be worried about. Okay? Any questions? Okay? The semicolon is your friend. Okay, our grading tentative breakdown here is about 36% midterms, 36% projects, 8% homework, 10% participation, which is things like sections and lecture and so on. No final exam. But 3 midterms, okay? So, woo! All right, the midterms, I'm still trying to get the classrooms, but tentatively they're in the 7 to 9 p.m. range. This is because Berkeley has some arcane rules about not being able to assign classrooms until after the 3rd to 5th week. I forget exactly what it is, for anything earlier than 7. So the best I can start with is to find 7 to 9. I will try to, probably not for the first one, but for the second 2, I will try to maybe move into our time slot. So if we could do a 5 to 7 midterm or something, that probably would work best. How many people think that's a good idea? Okay, so we'll see what we can do, and obviously there'll be overlaps and conflicts and stuff, but okay. So I don't need to mention that there is an honor code. So as a member of the UC Berkeley community, I act with honesty, integrity, and respect for others. I thought I would show you the fine print. We do run tools and unfortunately people get caught up in things like that every now and then. I would say just do your own work, okay? So explaining a concept to somebody in another group, discussing algorithms or testing strategies, helping debug somebody else's code in another group, searching online for generic algorithms. These things are probably okay because they're not directly doing the other person's project or using their code. Things that are not is like sharing actual code or test cases. Okay, copying or reading another group's code. Okay, that's probably not good. Copying or reading online code. So if you search and find code, just don't do it. Okay, just don't do it. It's very tempting, but it'll just get you caught up and it won't be worth the trouble. Believe me. It's just not worth it. Okay. And we compare project submissions against prior years and online solutions and so on. So, all right. Let me tell you a little bit about the typical lecture format for this class. So this lecture is completely different than normal. But let me tell you this. Let's see if I can find my little pen here. So, what did I do with my pen? Oh, there it is. So, the typical lecture format is the following. So years ago, we actually had somebody who knew something about how people learned, and they came and listened to our classes. And what they found was the first thing that all of the faculty did was they spent the first 15 minutes talking about organization of the class. Well, next Tuesday we're going to have a midterm. They'll be studying, and this following Friday, and homework 5 is due. And instead, really, what they said is, here's the way people typically act in a class. They start with very high attention, because you guys come in, you're all excited. It's a new class. Wouldn't this be wonderful? And what happens is people go and for about 20 minutes, and then, of course, what happens is your attention starts flagging a little. All right? So what we're going to typically do is we'll take a break where we'll talk about something interesting that happened in the news or something like that. And usually, that brings you back up again, right? And so then, you go for a while and then that kind of happens. And so actually what we do then is we let you get up and stand up and walk around, maybe go out to get a drink of water or whatever. And of course, that helps a little. And then we go, and here's the thing. You'll see that it's getting close to the end of the hour, but you got to wait for it, because what will happen is, yes, you're flagging, but wait for it, because I'll say, in conclusion, and at that point, wait for long enough for me to give a quick summary of what I did, and you can take that, that big spike in attention and walk away with some interesting things to summarize. And then, of course, you get to go out of the classroom. All right? So that's kind of what I'm going to do. So I try to divide things up into like 3 pieces. Today is an exception. But it's kind of like, with the break in between, just to give you a little bit of a better attention span. Okay? So it's like, minute review, 20-minute lecture, etc. Okay? Now, the goal is, of course, interactive. So again, this is a special lecture, but I love to have questions. Things are much more interesting if people ask me questions. I can answer questions. We can see where the class is. Gives me a way to understand the heartbeat of what you guys are thinking. And so, please, ask questions. All right? That's what I'm here for. All right? This is all about learning. And presumably your questions are often much more interesting than something I could say. But my answers, they're going to be great. So we talked earlier about what an operating system is. So we talked about the referee, illusionist, and glue pieces. Referee is managing resources. Illusionist is giving you clean abstractions, virtual abstractions. And glue is common services. All 3 of these things are typically in an operating system that you're likely to run on a laptop or even on a cell phone. When you start getting into those interesting little IoT devices like that, I kind of mentioned the idea of a temperature sensor or a video camera that's in the wall or something like that, not all of these functions may be there. Okay, so if it's a little device that's likely to have only one user running on it, then maybe there's no need for a referee to protect you. But maybe if there's 2 things running, maybe there's a need for good resource allocation to meet quality of service guarantees. Okay, and so you can mix and match some of these pieces or subset them as you get into the little devices. And we'll talk, as we go along, we'll talk about, when these pieces might be in something and when they might not. Okay? The challenge is always complexity. So applications consisting of a variety of software modules that run on a variety of devices, that implement different hardware architectures, run competing applications, fail in unexpected ways, can be under a variety of attacks. These are all things that add complexity. And so we're constantly trying to figure out how to trim the complexity, right? This is like a continuous haircut of functionality, okay? And and you can imagine I know something about haircuts, right? So it's really not feasible these days to even test software for all possible environments and combinations of components. There is so much complexity that the notion that you could somehow test for every failure is just off the table. Okay? It's just too complicated. Now, there's a lot of really interesting work in model-driven software development and a lot of these things where it's really about designing correctly the first time around. And we're going to try to approach that. Okay? We're going to try to understand how to design your software in the operating system context in a way where it's not a question about whether there are bugs, because obviously there are, but how serious are the bugs? Okay, and you'd like for the bugs that are left to be not as serious. Or if you think that something's going to have a lot of bugs, it's interesting to start talking about, can we containerize? Can we put a virtual machine around a piece of buggy software or suspect software from a malicious person out there? We can start containerizing things as well, and we'll talk more about that as we go. Okay? So the world, as I mentioned earlier, is parallel. So this in 2017, I grabbed this figure just because it was easy to get at the time. But here is, 3 years ago now, 28 cores, 58 threads on a chip. Okay, and imagine you put a bunch of these chips, okay, into a rack, and you put a bunch of racks into a warehouse scale cloud system. Holy Toledo, there is a lot of threads. Okay, there are a lot of things running simultaneously that you've got to somehow control. Okay, and there are lots of different instruction sets for security and graphics, etc. There's many caches. There's on-chip networks, off-chip interfaces, DRAM, etc. All of this complexity. So you could, A, run screaming into the other room because there's too much complexity, or B, you could say, isn't this cool? Let's figure out how to tame the complexity. Okay, we're going to talk about taming. So another thing that if you're really interested in the deep device driver aspect of operating systems, we're only going to touch on that, but I will say that the processor, despite what you might have learned in 61C, isn't really the interesting part. Okay, now I'm a computer architect and I love processors. It's far more interesting to look at this. See this diagram? We typically have the processor, which has some high-channel DRAMs and some graphics, but then there is a digital media interface down to this other thing, which actually has all the interesting stuff. Lots of I/O devices, okay? Audio and storage and USB drivers to go off to all your interesting stuff and so on. All of that goes off this bottom chip. That's the interesting thing, right? How does this system interact with the world? That's the bottom chip, and that's actually something with you, if you're really interested in device drivers, that gets pretty interesting pretty quickly and pretty complicated too. Okay. So the other thing is you can go to this website, which I kind of like to do every now and then. Information is beautiful.net, visualizations, million lines of code, and this shows you how much complexity there is in software these days. And if you look, the Linux 2 kernel is down here, but boy, as we get on through Firefox and Android and Windows 7, which is expired, by the way, as of a week ago, and we work our way down to some of these others, we get to things like Facebook and OS X Tiger, OS X 10, and then a modern car is up here at 100 million lines of code. And look, a mouse is 120 million lines of code. So that's a level of complexity that our software is at these days. I think that's kind of a fun virtualization or visualization to actually see. I wanted to give one example. So the Mars rover, how many people have ever heard of Pathfinder? This is an old story, but it's kind of interesting. So this was one of the first really successful rovers that was sent to Mars, and it had a really interesting delivery system. So, you know, you probably think, well, this thing goes to Mars and it lands using rockets so that it touched down lightly on the ground. No, that's not what they did. That's too complicated. What they did was they took this item, once it was in orbit around Mars, they had to get there first, they put a huge balloon around it and they bounced it. Okay, they dumped it out of the atmosphere, it bounced on the ground, it bounced a few times, they opened it up, and then it drove away. So what a delivery system, okay? But this particular Pathfinder had very limited statistics, but it could do all sorts of stuff. It had cameras and scientific instruments, and of course there were batteries and solar panels and locomotion equipment to get it around. And the downside was you couldn't hit the reset button very easily. Okay, it's not like you can say, you know, reboot, Control-Alt-Delete, or whatever your current reboot technology is, right? So this is a great instance of why you've got to design really well-structured software that won't fail. And the individual programs themselves shouldn't fail. So suppose the Martian Universal Translator, to talk to the Martians, better not crash the antenna positioning software because while it's busy talking to Martians, If the antenna is not pointed directly at the Earth, then you can no longer talk to the rover and you're in trouble, right? And so also software may crash occasionally, so you need to have some way of automatically restarting and sending diagnostics to Earth. And, certain functions are time critical, like don't run into things, okay? You've got to stop the rover before it goes off a cliff. So it is kind of interesting to think about that level of technology and the Internet of Things where the devices have more complexity than that rover did, and there's potentially many of them out there that nobody can actually reboot. And so some of the lessons from the Mars rover might start to impinge how we design these devices. There is some interesting story, which will be for another lecture, about how this particular rover got into a priority inversion problem that basically caused it to crash on a regular basis. And they managed to debug it and upload a patch and fix it from Earth, which is pretty amazing. Okay. So how do you tame complexity? Every piece of computer hardware is different CPUs, different amounts of memory, disk, different types of devices, different networking environments. The question is, does the programmer need to write a single program that performs many independent activities? Potentially. Does the program have to be altered for every piece of hardware? Better not. Right? Think about that. If every version of you had to write a separate version of every program to deal with a slightly different disk drive or a slightly different amount of memory, that would be ridiculous. And so really, you can then say, does a faulty program have to crash everything? That also shouldn't be true. So these are some of the complexity taming questions that we're going to start asking. Does every program have access to all pieces of hardware? Probably not, right? That's a good way to cause things to crash. And so we're going to basically talk about, from early on in this class, this idea of a virtual machine abstraction where the operating system hides the messiness of the hardware from the application. And that's going to be a meme. Okay, hashtag virtual machine. Okay? This is going to be what we're going to do to try to make this work. By the way, my son, who's 8, has been somehow saying hashtag everything right now, and I don't think he even understands what that means, which is pretty... Hashtag OS tool. Anyway, we're going to talk a lot about virtual machines, different types. We'll talk about process VMs, and we'll talk about fault isolation and how VMs help you with that. And I'm not going to do more about that today because we're running low on time, but I am going to say, in conclusion... Operating systems provide a virtual machine abstraction to hide diverse hardware. We started talking about that. Operating systems simplify application development by providing shared services. They coordinate resources and protect users from each other. Okay? And basically, CS162 is going to combine things from many areas of computer science. Languages, data structures, hardware, algorithms, security, you name it, we will touch on it. All right, you guys get working on homework 0. Do we have an ETA? Midnight. See you guys on Thursday.